Okay, let's talk about divisibility. Prove that a three-digit number. Prove that a three-digit. That was messy. Number is divisible by 3 if and only if. Oh, we're not like 2 f's at this point. If and only if the sum of its digits is divisible by 3. Okay. Okay.
So what is that? So you prove that a
Three-digit number. Yeah, that was a bit messy, that word. I don't know why it went that messy today, but it did. A three-digit number. I've made it worse. Prove that a three-digit number is divisible by 3 if and only if the sum of its digits is divisible by 3. Who knew this already? And you can check whether the number is divisible by 3 by adding up the digits.
I remember learning that in year 2, but
it's from that sort of time.
Whatsoever.
It's that sort of time ago. How do I know if this number is divisible by 3? Out of the digits. Are they divisible by 3? 8, 16, 19, 28, 29, not divisible by 3.
So if you add
Therefore 3 doesn't divide this.
Well, if you just get rid of either of the ones, then it is.
Sorry?
If you get rid of either of the ones.
Sure. You don't know that rule. Well, now you do. We're going to prove it. We're going to prove it. Okay. Let n be a number. Actually, do I have to preface this with which direction I'm going? Oh. With digits A, B, C in order. So n is my big number and its digits are A, B, C. It says if and only if, so I'm going to prove it in both directions. First, suppose n is divisible by 3. Yep. N is divisible by 3. How can I write that using some maths? That is n, wait, it's the digit, so it's n is equal to 100a plus 10b plus c. And that has to equal 3 times something. What did they use? K. Nice. Where k is some integer. You agree with that? If n is divisible by 3, then it's 3 times some integer. I want to know about the sum of its digits. So I want to get something that goes A plus B plus C. Well, if I've got 3k on this side, I don't want to change it yet. I've taken out an A and a B from here. I'm left with 99A and 9b plus a plus b plus c. This is what I want to know about. It's what I'm aiming for. sum of the digits. Well, leave those there and put these on the other side. A plus B plus C must be 3k minus 99a minus 9b. Apparently I shouldn't have used A and B and 9s because they all start looking very similar. Can you see what I'm going to do next? I want to prove that the sum of the digits is divisible by 3. Well, I can factorise 3 out here, can't I? K minus 33a minus 3b. But K and A and B are all integers, which means this is 3 times an integer, which means 3 must divide this. But K minus 33a minus 3b is an integer, therefore 3 must divide a plus b plus c. Have I finished yet? No. I have proved that if it's divisible by 3, then the sum of its digits is divisible by 3. But I have to prove if and only if, so I have to prove the other direction. Second, let's now suppose A plus B plus C equals 3 something. I bet they used K again. Let's use a different letter so you don't get confused. 3m, where m is some integer. It might not be the same as this k, some integer. Can we get back to this being true?
Are we allowed to just do the exact same working but backwards?
Sometimes. As long as everything here is just equals, 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 yes. But if in here you've got an implies, and be very careful with less thans and greater thans, you may not be able to go easily go back. So be careful. Sometimes you can. They've said, here we're going to go, well, n we know is 100a plus 10b plus c. Yes? This is not quite exactly going back, but it's related to it. We know that's my number, and we know that a plus b plus c is 3m. So let's again get that separately. Plus a plus b plus c, and what have I got left? I have 99a and 9b. Well, that's 99a plus 9b plus 3 times something. Using my assumption up here. Oh, wait a minute. I can divide everything there by 3. Let's factorise. 3 times 33a plus 3b plus m. See how it's similar? It's not exactly the same as going backwards, but it's very similar. But 33a plus 3b plus m has to be an integer, and therefore 3 must divide m. We proved it both ways, QED.